Overview of Electronics 4.0 for a SelfieBot model set. Electronics 4.0 is built on the basis of two circuit boards, a microcontroller board and a power board. There are two boards are connected and exchange data with each other. It is even possible to say that they control each other. Each of them looks like this breadboard with soldered connectors for modules. We see connecting wires, SMD resistors under the board, and various connectors, field effect transistors, optocouples, resistors, fuses, and the other part of the board. On the microcontroller board, we also see various connectors for external devices as well, configuration jumper and connecting wires for various elements on electronics on the opposite side. Now, let's assemble the power board. First of all, it is necessary to explain what the set of electronics consists of. Two boards, first and foremost. We install a voltage converter on the power board. The computing core of our system is a microcontroller, which is connected to the Bluetooth model, a port replicator, an ambient light sensor, a motion sensor, a current sensor based on the Hall effect is connected to the power board. We also connected this unit with an attached lithium-ion batteries controller. This unit contains 3 lithium batteries 18650, already known to us MG996R servos, and a set of different cables for light buttons and connection of the board with each other. All these items make an electronics package. Power board assembly. A power board. We mount DC-DC converters on the power board and connect a Hall effect sensor and a battery unit to it. We need cables to control this board. According to the instruction, we connect all the necessary modules and mount them all on the power board. Each board and each connector has alike painted keys to avoid connection errors when installing modules. So we are installing this DC converter in accordance with the mount key, and will do the same with the rest of DC converter models. The first row, power converters of USB 1, USB 2, and those of the board with a microcontroller. In accordance with the key, we horizontally mount a module to power the server. The button to activate the entire device has no key. Polarity is not important. According to the schematics, we connected to certain pins of the side row of connectors. The battery unit also has a key. We connect it with the connectors in accordance with the schematics. The power connector has these wires, 2 of which power the device, while the third is signal measuring wire and tells microcontroller about connection of the power supply unit. A Hall effect sensor. We connect a Hall effect sensor to the board according to the schematics, and the key. After that we mount a DC-DC converter. On the opposite side of the Hall effect sensor there are 2 3-pin connectors, a 2-pin connector and 3-pin one. To be precise, in the middle of each pin stopping plug to avoid wire connector connection error. The key, a painted part of the pin, which is the ground in the power supply of the connection in this case. Ensure foolproofing and minimizes risk to spoil everything. The last side connector serves for connection of the thick cable necessary to organize interplay of both boards. This cable supplies the microcontroller board with necessary power, telemetric signals and control signals for cascade connection of transistors or DC converters. Thus we have assembled the power board. Microcontroller board assembling. Here we also use painted connectors keys. We mount the models according to the schematics. With the key in view, we install microcontroller, a light sensor, a board of microcontroller ports, expander, a Bluetooth model, a jumper. After that, we have only a big connector for the power board and a number of small ones for peripherals. According to the schematics, we connect two servos and the light sensor connector. We use simple photoresistor. A photodiode can be used as well. Here the polarity matters. When a motion sensor turns come, it's important detail. A light sensor has a turning calibration resistor, but to calibrate the sensor it's not necessary. Because of the 4 terminals there is an analog output and digital one. This calibration is for the digital one, but the microcontroller digitalizes the analog output of the sensor, so the setting of this board is not needed, but the motion sensor model getting is required. There are 2 resistors, a resistor of the sensor operation sensitivity set in the middle, and the other is a resistor of pulse duration at the motion detection. It is set to minimum. There is enough for microcontroller because it's the microcontroller, not the sensor, that counts timeout at motion detector. So we connect the sensor to the connector of the microcontroller board in accordance with the key and schematic. The next connector is a LED. Then we connect the user button. One more untapped connector is left. The connector is meant for an external load. At command going from the external device via Bluetooth, this microcontroller board will apply 5 volts to this connector, thus extending functionality of this board, as it's possible not just to connect mentioned sensors, but also to connect additional external peripherals such as infrared lighting on the basis of the information received from the light sensor or motion sensor. The first start and connection via Bluetooth. Let's join our both assembled boards, the power board with the microcontroller board, and try to turn on the power of the device. First of all, we'll see the light on the LED. It means that battery applies voltage to the power board. 2 LEDs of the DC convert glow on the power board, forming 5 volts from the electronics and 7 volts for the servos. When the green light of the LEDs is not blinking, it means that the voltage from the battery is enough for the entire electronic works at the board start. Now let's turn off and turn on the power. The LED will glow white, then blink green 3 times, glow white and green again. The white light means that start and end of initiating process. The green flickers means testing of peripherals, connecting and setting of Bluetooth model and successful power supply to the servos. Let's now connect the device to the control panel. To operate this version of the electronics, we created a virtual control panel in the LabVIEW program and called it SelfieBot Control Panel 1.0. It's worthwhile mentioning that a Bluetooth controller has been already installed in the device. Using the Windows tool, we connected the Bluetooth model with the Bluetooth Windows controller. Now we see the red light on the controller LED flickering. As the Bluetooth model connected to the Bluetooth Windows controller, Windows gave me COM15 for serious connection. Consequently, I select port 15 on the SelfieBot panel and establish connection. Bluetooth model light stops flickering and now glowing. It means the standby charge to the connection mode and established the connection. Now let's check the board. The virtual panel presents 3 columns. First, COM port number and device parameter setup. Second, command setup and issuing. Third, telemetry decoding. I select the telemetry request, send it and receive the answer. The telemetry code, the indicator light shows that the telemetry structure is correct. That is, all command boxes in the code are correct. The firmware code is 01. On the basis of the code, the control panel detects that the software version 3 4.0. So it happened that all our control software versions are one number less than the electronics version. So if the electronics version is 4.0, then the firmware version is 3.0. The initiating process 0B says that the connection via Bluetooth and its setup went out without a hitch. The servo power check was successful. The Bluetooth model named SelfieBot -XX is loaded by default. Actually, the initiation code is the code confirmation of the green LED flickering at the electronic start. That is what we saw when turned on the power. The next block tells us about the battery condition. We see that the charge of the battery is good. No external power supply is connected. The battery voltage is 12 volts. The battery current is minus 0.43 amps. The minus means that the battery is discharged. The next block is the code of servo position. The setup 90 degrees by default. At the very bottom we see the telemetry data of the light sensor. It displays the voltage when it is very light, the voltage tends to go to 0. The darker is the voltage is higher. The code of the presence device status shows that the servos are powered, the auto electrical connection control is off, and there is no external power, and external charger is not connected. The battery unit charge is good. The USB power supply and the power supply load are off. The motion sensor telemetry says that some kind of movement was detected about a minute ago and the user button is off. Device operation. Let's try to operate the device using the virtual control panel. I set the horizontal servo to 0 and the vertical one to 180. Disable formation of the telemetry request code, activate formation of the horizontal and vertical servos control code. Set up the selected values. Send the command, then disable formation at the servos code. Turn on the telemetry request code and request the telemetry. Here we see that one servo turned to 5 degree instead of 0 and the second to 175 instead of 183. There are 3 degree angles. Are protective angles are controlled at the level of the firmware. That is, they do not allow the servos to take the extreme position. Further, using the control panel, we can supply power to the end connector of the microcontroller board from the external source. To do this, we turn on power on the control panel. Choose the corresponding command to set up parameters and send the command. Then we request the telemetry and see that external load power is on. This connector voltage is now 5 volts. Now let's check the user button. It's off now. I press it and the telemetry request on the control panel displays shows that it's on. The Bluetooth model operation. The Bluetooth model name entry. This virtual control panel allows programming the name of the device as the Bluetooth model name. Now it's loaded by default as SelfieBot -XX. There is a special field for the Bluetooth model where you can enter any name and program it. To upgrade the firmware, I set up the name of the model of the command code formation selector. Enter the Bluetooth model name and sends this command 3 times. After the 3rd time, we see that LED flickers blue. It means that the Bluetooth model name has been successfully programmed. Let's initiate the model once again. We have to disconnect from the COM port, then turn off, and on the electronics on the board connect the Bluetooth model and request the telemetry. In the initiation section, we see that Bluetooth model setup has been successful. The servos are powered, the Bluetooth model username loaded to the memory on the device earlier, it's saved. So if I connect my phone to the Bluetooth model, I will have to look for the original name we gave it. We can erase this name and program other one or restore the default name. It's easy. Just select the Bluetooth default name, select in the command formation and send the command 3 times. The LED will flicker blue, then white and green. The blue light informs about programming of the Bluetooth model name, and the following white light tells that the default name is set. These simple settings help check the electronic health. Now let's digress into more interesting subject, power check. To demonstrate the functionality of this version of the electronics and microcontroller firmware when working with power, I disconnect the battery and connect a controlled power supply. Let's turn on the electronics connected to our control panel and ask for the telemetry. According to the telemetry, we see that the battery current is negative. It means it's being discharged. The current of the 200 milliamps and the voltage 11.7 volt. Now I'll deliberately lower the voltage down to 10.26 volts. The LED light is still green. The electronics believes so far that it's alright. I reduce the voltage again. The LED flashes red once per second. According to the telemetry, we see that the battery voltage is 8.7 volts. The red light indicates that the battery requires charging. If I go back to the original level of the voltage value, the telemetry reports that the level of the battery voltage is normal, but the operation of the device will be blocked because of incomprehensive voltage drop was recorded earlier. Therefore, the battery requires recharging. In this mode, all the device operation commands are blocked by the telemetry request. The telemetry request command is always executed. When connecting to the external power supply, voltage is applied to the servos and the red light changes to green, flashing with the same frequency. All DC converters of the power board are turned on. The electronics applies voltage to its USB output. Using flashing of the LED indicates that the battery is charging. Unfortunately, the picture I see now is not quite correct. To make it correct, it is necessary to discharge the battery to a minimum. Now the telemetry shows the light of the connected external power supply, but the battery unit is negative as if it's being discharged. This is due to the fact that instead of the battery unit, I connected an external power supply. To correct this picture, I turn off the electronics and disconnect an adjustable current source. Reconnect the battery unit and turn on the electronics. We connect it via Bluetooth. After connecting, we request the telemetry. The voltage of the battery unit is 11.8 volts. The battery current is negative and therefore it's being discharged. I connect the external power supply. The LED begins to flash green. In response to the telemetry request, I see the light of the external power. The voltage jumps to 12.4 volts. This is not the battery voltage, but the voltage of the external power supply. The light of the external power supply is on. The battery current is about 160–180 milliamps. This indicates the battery is charging. The less is the battery charge, the higher is the value of the current. We can determine the battery charge by the electric current intensity. Below, in the section of the device status, we can see what is now going on. An external power supply is connected, the battery unit is charging, the USB devices are powered. The electronics control is not only the charger connection, but also the quality of the external power supply. To demonstrate this, I need again to reconnect my external power supply. I turn off the electronics, connect the battery unit and in external source of controlled power. After turning on the electronics, I connect it via Bluetooth and request the telemetry. The battery provides 12.0 volts and is being discharged. Now I connect the external power supply and ask for the telemetry. The telemetry says that the external power supply is connected and the battery is charging. Suppose we have a bad supply. At first it gives its required 12.4 volts, then the voltage starts suddenly to fall, then it drops to 11.7, then 11.3, and then drops below 11. The electronics records the fact and the red light starts flashing 3 times per second. If the voltage returns to the specified range, the battery unit will begin charging again. Thus, the quality voltage issued by external power source is controlled.